Hi class, today's lesson is on covalent molecules. So we've already talked about ionic compounds before, and an ionic compound is when you have a cation and an anion. Another way to think about this oftentimes is when you have a metal and a nonmetal. So that's one type of bond, and we spent a couple of days doing that. Now today, the new one is called a covalent molecule. Spelling that wrong. And a covalent molecule is when you have two or more non-metals. So there's only non-metals in covalent bonds. For ionic bonds, sorry, we're going back and forth here, but for ionic bonds, the atoms, a cation and an anion, were able to form a bond due to a transfer of electrons. And we drew arrows to represent that on Lewis diagrams. But for covalent molecules, it works differently. This is actually done by sharing of electrons. So every atom is trying to get 8 valence electrons. If we're talking about nonmetals, that is, they're all trying to get 8 nonmetals, except 8 valence electrons, except for hydrogen, which only needs to get 2. Now, one way to get the 8 electrons is to take electrons away from cations, but it turns out there's another way to obtain 8 electrons, and 2 or more nonmetals can actually share electrons, so they both have access to it. So we're going to go into some examples. We'll start with ones you've already heard of. So carbon dioxide is probably something you've already heard of. And carbon dioxide, you may know the formula for it already. It is CO2. And that means there's one carbon atom for every 2 oxygen atoms. So if I start drawing Lewis diagrams of 1 carbon and 2 oxygens, here's my carbon. It's in group 14, so there's 4 valence electrons. And I'm going to draw an oxygen on the left side, the right side of it. And I'm going to draw an oxygen on the left side of it. And oxygen has 6 valence electrons. Now, I actually drew the electrons in a strategic way. So what ends up happening in a covalent compound is that the 3 atoms here, they're going to work together and share pairs of electrons. So I'm going to circle one sharing pair here. So you have 1 electron from oxygen is going to kind of pair up with 1 electron from carbon. And the atoms are going to get so close to each other that both the oxygen and the carbon have access to both of those electrons that I just circled. I'm going to share another pair down at the bottom here. These 2 electrons will be shared between the atoms. And then on the right side, we'll have these 2 electrons get shared between the atoms. And then finally, these 2 electrons that I'm circling get shared between the atoms. So if we count how many electrons each atom has access to, we should actually end up with 8 for everything. So I'll start with the oxygen on the left. I'm going to start counting electrons it has access to. 1, 2, 3, 4. Now 5, 6, because it has access to both of those in that circle. And then 7, 8 has access to both of those in that circle too. So that oxygen atom has 8 electrons it has access to. So it has access to its own electrons plus a couple more from carbon that it is sharing. So it's considered to have a full valence shell now. Now I'll do the same kind of counting, but for the carbon. Okay, so the carbon is actually sharing all its electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Carbon has access to all 8 of those electrons. So it's also considered to have a full valence shell. It is stable and happy. And now I'm going to count the electrons that the oxygen on the right side has access to. Okay, so its own electrons first, 1, 2, 3, 4. And now shared electrons, 5, 6, 7, 8. Okay, oxygen has access to those 8 electrons. So it is full, it is stable as well. So that's how nonmetals can work together to share electrons. And they will stick close to each other because of that. And so we say they make a bond with each other. And it's called a covalent bond. Covalent, I guess, meaning valent, standing for valence electrons. And co, I guess, is standing for sharing. They're kind of able to share valence electrons. So the diagram I drew, I'm going to call it sharing diagram, electron sharing diagram. And that's different than ionic. Ionic, it's called an electron transfer diagram. For sharing diagrams, there's another way to draw it. So another way to draw it is to replace shared pairs of electrons with bars. So every time I see one of these, 2 electrons shared together, I'm going to replace it with a bar. So I'll replace it with that bar. And then there's another one here that's a shared pair of electrons. I'm going to replace it with a bar connecting carbon with the right-hand oxygen. There's 2 more bars I'm going to draw on the bond on the left for those 2 shared pairs of electrons. And then I'm going to draw the electrons that are not shared. So oxygen on the left has 4 unshared electrons, and the oxygen on the right also has 4 unshared electrons. So this is a more neater way to draw covalent bonds, actually, is to use these bars. Every bar represents 2 electrons. And both of the elements that the bar is connecting, they both have access to the 2 electrons. So this diagram is called a structural diagram. It's called a structural diagram. Okay, so a sharing diagram has circled up pairs of electrons, and in a structural diagram, they have bars. Okay, now, why is it called carbon dioxide? Well, when we're naming covalent compounds, we use prefixes. And the prefixes, they match with how many atoms you see of that kind. So di is a prefix for 2. So dioxide means 2 oxygens. And there is only 1 carbon, so we write carbon. Now there is a prefix for 1, and it's called mono, but we never start with a mono. There's just kind of a rule. We never start the name of a compound with mono. So this is called carbon dioxide. Okay, we're going to do a bunch more examples. Okay, so I'm going to do hydrogen. I'm spelling wrong today. Hydrogen monofluoride. I'm going to try that. Hydrogen monofluoride. So if we look at prefixes, hydrogen doesn't have any prefix, so we're going to assume it's 1. And mono is a prefix for 1 as well. Okay, so in a 2-word name, you do not have to write mono for the first word, but you do have to write mono for the second word. So there's one hydrogen, one fluorine. That HF would be the chemical formula for hydrogen monofluoride. Now, the sharing diagram will look as follows. We have hydrogen's Lewis diagram, just one electron. Fluorine is a halogen, so fluorine has 7 valence electrons. Now, strategically, I'm going to draw the single electron close to the single electron of the hydrogen. That way, it's easier to circle the shared pair up. These two are going to end up sharing. So hydrogen will now have access to 2 electrons, and so it actually has a full outer shell now because 2 electrons is all it takes to fill up its first shell. And fluorine now has access to 8 valence electrons. So both of these atoms are now stable. So they have made a covalent bond. Now this is called the sharing diagram. And what was the other diagram called again? It was called a structural diagram. And that's when we replace the shared pair of electrons with a bar. Okay, so there is another example, HF. All right, let's see. Okay, I am going to go with dicarbon hexabromide. Dicarbon hexabromide. So, I've already talked about the prefix di. That means 2. So there's 2 carbons here. And what do you think about hexa? Have you heard the prefix hexa before? You may think hexagon. So that's a 6-sided shape. So hexa actually stands for 6. All right, so the chemical formula here is C2, and then bromine is Br6. Okay, so that's how the prefixes work. Okay, so let's try to draw it out. I need to draw 2 carbons. 1, 2. Carbon has 4 valence electrons. And now I need to draw 6 bromines. Bromine, if you find it on the periodic table, it's a halogen. It's in column 17. So it will have 7 valence electrons. Now, I'm going to think ahead a little bit. I'm pretty sure these 2 electrons of the carbons next to each other are going to pair up. So each carbon has 3 spots left that need a partner. So I'm going to strategically draw the bromines with 7 electrons, but with the 1 electron right next to one of the lonely electrons from carbon. Okay, so all these bromines, I'm drawing 7 dots for each of them strategically so that the 1 leftover dot is right next to one of the leftover carbon dots. That makes them really easy to circle up. Okay, so that's how that one's going to work. And if you count, every atom here actually has access to 8 valence electrons. So it's stabilized. I've drawn the sharing diagram. I can now draw the structural diagram. Which is a little cleaner than the sharing diagram. All those red circles I'm replacing with these bars. Okay. Let's keep going. So far, in terms of naming these covalent compounds, there's some similarities to naming ionic compounds, but some differences as well. Um, Actually, maybe I'll make a T-chart. So ionic naming, or just names, covalent names. Okay, so what they both have in common is that you just write down the regular name of the first element. Uh, this might not be the most efficient way to do this, but whatever. Okay, regular name of first element. So they have that in common. Another thing they have in common is that we change the ending of the second element to IDE. Okay, so those are the two similarities. Um, Now, differences for ionic compounds, since they have multivalent metals, sometimes you sometimes need a Roman numeral. Okay, so for things like iron, copper, tin, lead, those are all multivalent metals, and you will need a Roman numeral when naming them. And in covalent compound, you will never use Roman numerals. However, for covalent compounds, you need to use prefixes. Whereas for ionic, you never use prefixes. For covalent, you always use prefixes, except we do not use mono for the first element. That's the only one we skip. Okay, so those are the differences between naming ionic versus covalent. So you'll be expected to name them, write the formulas for them, draw sharing diagrams for them, and draw structural diagrams for them. Now, there are special covalent molecules called diatomic molecules. Diatomic molecules. So a diatomic molecule, you may guess from the prefix di that there's two atoms. And it turns out that it's a bond between two of the same atoms. And it's a covalent bond. Well, it has to be a covalent bond. A covalent bond between two of the same elements. And there's only a small number of them. So I'll list all the ones that exist here. There's N2, O2, F2, Cl2, Br2, I2. I feel like I'm missing one. Oh, yes. H2. I missed the simplest one. Okay. These are called the diatomic molecules. Now, we often call, these are all gases actually. So we actually give them names simply as nitrogen gas. And O2, we simply call it oxygen gas. And same with every single one of these. F2 is called fluorine gas. Cl2 is called chlorine gas. And then Br2 is bromine gas, and then iodine gas, and then H2 is hydrogen gas. I'm not going to write all those down, but we just call them their regular name and then the word gas. Sometimes you may find me calling it like something, difluorine. I might call it difluoride. If I say that, I mean the same thing as fluorine gas, F2. Okay, but I should be calling them all gas. So these are all molecules, but not compounds. So this is a terminology thing here. Molecule is when you have two or more atoms bonded. A compound is when you have two or more different atoms bonded. Okay, so O2, it's, for example, two oxygens. It's two atoms, but they're the same atom. So we can only call it a molecule. We cannot call it a compound. Okay, CO2, though, carbon dioxide, that's also a molecule, and we can also call that one a compound. Okay, so it's just a terminology thing. Okay, so let me draw one. I'll draw nitrogen gas. Let's say, I'll use this as an example. So N2 means I have to draw two nitrogens. Nitrogen, I know, has 5 valence electrons. So I'm going to strategically draw them in a way that I can easily circle up electrons that should be paired. So if I put 2 electrons on the far side and then the single electrons on the top, the bottom, and the right, I'll do a similar thing for the other nitrogen, this time putting the 2 electrons on the far side. Drawing it this way makes electrons easy to circle up to be shared. Just like so. Okay, so that's the sharing diagram for nitrogen gas. And we can replace it with a structural diagram. So now I have to draw 3 bars to replace the 3 circles. Okay, this is called a triple bond. If you have 3 bars connecting 2 elements like that, it's a triple bond. If you have 2 bars connecting it, it's called a double bond. And 1 bar is called a single bond. Okay, so that's the diagram for nitrogen gas. The prefixes, so if you're not used to prefixes, mono, we've talked about, it means 1. Di is 2. If you ever come across 3, you'll use the prefix tri. You come across 4, use the prefix tetra. 5, we'll use penta. And 6, we'll use hexa. For the last 3, tetra, penta, and hexa, if the word that follows it starts with a vowel, we may drop the A in tetra, penta, and hexa. Okay, so drop the A if the next element begins with a vowel. So that usually happens with oxygen. So for example, let's say CCl4, that would be called carbon tetrafluoride. Okay, so we keep the, sorry, not fluoride, chloride. So we keep the A on tetra because chloride, it starts with a consonant. But if something starts with a vowel, like let's say C2O4, that would be dicarbon tetroxide. We drop the A if the next one starts with the vowel, and we just go tetroxide. Okay, so I think that should be it. That should be enough to do your homework for today, which is in the a document, though you should be given a handout because you'll have to draw these diagrams, and that's difficult to do on the computer. Okay, so please complete the worksheet for homework.